Yes. So now it is recording. Hi, team. Hi, everyone. And so, yeah, today we have Tim Hudson. He's a hydrologist at the USGS Central Midwest Water Science Center in Urbana-Champaign, Illinois. And he's our speaker today. He will be discussing his recent paper on how to select an objective function using information theory. So welcome, Tim, and the floor is all yours.
Thanks for the introduction. I know some of this is double booked, and here I am sitting on the floor. But fortunately, it's a short paper and pretty straightforward. So I think we can be through this in half an hour or less. But I'd like to begin just sort of how the paper came about and thinking about Nash-Sutcliffe efficiency. And in the paper, I try not to recommend any specific objective functions and leave that to the user. The choice depends on your problem. But that said, I'd like to begin just speculating a little bit about Nash-Sutcliffe in R squared. And as we get into the paper, some of this will be brought home with a some of these feelings. And I'm sure many of us have shared feelings about the use of these metrics. The classic justification for Nash-Sutcliffe goes along the lines that it penalizes inaccuracy at high flows. And that's useful because high flows are usually what's economically important for our model-based argument. But I'd like to kind of put it to everyone to take a moment. Given what you know about streamflow data, what might introduce noise if we're using the Nash-Sutcliffe? Anyone? It's that streamflow data themselves have uncertainty. In fact, the data that USGS generates that many of you use isn't actually an observation, right? It's an output of another model, a rating curve. Usually we would measure something like stage as a surrogate. And occasionally we'll go and collect a discharge measurements to calibrate that rating. And those measurements themselves have an inherent uncertainty, which grow at higher flows. But furthermore, high flows are often estimated by less accurate methods, like slope area, which can have 30, 50% uncertainty. We don't really know how to quantify it, but it can be large. And finally, we are allowed to extrapolate those rating curves twice beyond the largest observed flow. Okay, there can be a substantial uncertainty at the upper end. And the same goes for a lot of the hydroclimate forcings that we use. They can have small errors and biases. Precipitation undercatch is one example. But the point of this is, in effect, Nash-Sutcliffe, in calibrating to the highest flows, is calibrating to noise. And you can still make arguments that this is it's valuable to you to calibrate to high flows in this manner, but this sort of noise is almost inescapable. And this paper hopefully provides some tools to equip us to take some alternative approaches. And finally, just kind of summing up the sentiment, I've been fortunate enough to have gone through all the hydro-MLs, and I don't want to pigeonhole anyone, but I kind of felt like the sentiment in 22 was, wow, these ML models are great. They're more accurate than our physics-based models. And so maybe, the conclusion is that these models are learning better physics. And I think in the past couple of years, that attitude is changing, and maybe ML is learning something other than physics. And should we care? I'll leave that question open, and maybe we'll discuss at the end. Okay, so my role at USGS, a lot of my work focuses on topic of model evaluation, benchmarking, how we can come up with rigorous systems for evaluating our models, uncertainty, probabilistic modeling. So I spend a fair bit of time learning about this stuff I still have much to learn. But the question that I'm kind of faced with is, given a general purpose model, like a large land system model, a national hydrologic model, an LLM, how do we go about evaluating that thing? There's two pairs. The first, we use a loss function for minimizing economic losses in a particular context, right? That's the Nash-Sutcliffe justification. But with these general models in particular, it's almost impossible to define value in a meaningful way. People have conflicting values. You have how do you measure the values of 1 billion people and somehow incorporate that to a model? So the alternative paradigm is the information theoretic or the Bayesian. That kind of very similar in my opinion. And in that case, we use an objective function. I don't know that this is official terminology, but I'm kind of playing with words. This function is meant to be an objective function as opposed to a subjective. And our goal here is to maximize information in our models or conversely minimize their uncertainty. And in this sort of paradigm, we can still make loss-based decisions, but typically we first calibrate for information. And then once we have this sort of optimal model, then we can apply a loss function in our decision making. I won't talk too much about that today, but that is generally how value is taken into account. And often these two paradigms correspond with different approaches to modeling from the outset. Deterministic modelers start from physics. Stochastic modelers start from probability distributions. And again, sort of at the root of this talk, you might be a deterministic modeler if you're using R-squared for everything. And that's a bad idea. And Anscombe's quartet is sort of the classic example of this, where each of these data sets has the same R-squared and many other statistical properties. But only in that first case, the top or left corner, is the R-squared, really meaningful in the sense that when we evaluate these models by R-squared, the others kind of diverge from some of the implicit assumptions. Higher R-squared doesn't necessarily mean a more likely model in these other cases. And that's something we should be aware of. Information theoretic modeling, our objective, as I said, is to minimize information loss, minimize our uncertainty. And we do that with the Kullback-Leibler divergence, loss when to approximate another model G. So first we need a method to estimate that. And there are two, I think often categorized as, differential versus discrete methods. I kind of prefer, at least in this context, maybe parametric and non-parametric methods. And parametric being where we assume a sort of standard parametric to compute the information, the normal, the log normal, the loss, etc. And then the non-parametric ones traditionally being things like histogram, binning, areas, neighbors, etc. And I think they're both great. They have strengths and weaknesses. With this talk, we'll focus on the former, but I certainly don't want to disparage the latter. And just quickly, I think there's one example of strengths of parametric methods. They often have analytical solutions. They have many fewer parameters, which is nice in high dimensional problems. Say if you have a model with 10 variables, right? And you want to represent the uncertainty, albeit imperfectly with say a normal distribution or something in that family. It only requires 55 parameters. Whereas if you were using binning, 10 bins in each dimension, you'd need 10 billion. So in these high dimensional problems, parametric becomes essential. Okay. So about 100 years ago, Fisher introduced this method of maximum likelihood. And these ideas had been bubbling well before him, but I mean, Fisher was certainly seminal in all of this. And about 50 years ago, a gentleman by the name of Akaike finds a simple relationship between this KL information concept and Fisher's maximized log likelihood. And these are the first sort of two main papers about it. And the titles kind of give you a sense, information theory and an extension of the maximum likelihood principle, a new look at statistical model identification. And the first paper, I think it was presented at the second symposium on information theory there in 1971, published a couple of years later. And he starts to sort of formulate these ideas. And it wasn't until later in 74 when things become a little more formalized. And so it's that 74 paper that people often cite. And then 25 years ago, two gentlemen by the name of Burnham Anderson wrote a great textbook, basically all about the application of Akaike's work. It's called A Practical Information Theoretic Approach. And I want to plug these two guys, not just because they were at USGS, but they were ecologists. So they're USGS researchers in the ecological unit. Many of sort of, I think, the best sort of earth science-y textbooks that treat information theory, probability theory, are coming out of ecology, and many of them by USGS researchers. And I think the reason for this is pretty straightforward, is that ecology has a very strong empirical tradition. You know, we're going out, we're collecting data, we're trying to come up with models to represent that, but they recognize from the outset that there's a lot of uncertainty. Their models will always be far too simple to represent nature adequately. And so uncertainty in their style of modeling, which I think contrasts a lot of what's been done in other domains of earth science, where we often begin with physics. And I don't know that that's necessarily hubris, but it has a lot to do with our educational background. Increasingly realizing that, many of these systems are and our brains can sort of represent with physics and with the data we have. And so uncertainty is increasingly important. And more recently, so, I think we're all familiar, there's been criticism of Nash, Sutcliffe, and R-squared, that they kind of remain standard metrics. And there's somewhat of a cottage industry coming up with alternatives. And I think in many cases, these papers can have very good ideas, but sometimes they're lacking in formal theory and benchmarking, which we need if we want to make progress. We need to know why is one better than another. And that's really what this paper that I reciting what Akaike and many others already in ecology already knew. So the paper is How to Select Your Objective Function. I also wanted to plug Jasper Brute in his recent paper that came out in June. Just sort of two examples of people trying to bring more of these ideas about probability theory. And again, not that there haven't been many others, but I think there's still room for more of this in earth science. So the paper attempts to summarize some of these main points of statistical theory, and then, as I said, demonstrate a basic method. And in a nutshell, so basic problem in modeling is our choice of objective function or performance metric. How do we decide whether one model is better than another? According to information theory, the best objective function is the one that minimizes information loss. And we can evaluate that with AIC. There are other ways to do it, but AIC, as we'll see, is an extremely pragmatic choice and should work pretty well in this application. And if you want to understand why this is important, I kind of liken it to friction. That information loss just creates a general inefficiency that incurs costs, however our model will be used. And we'll explore some of those ideas more. I don't, demonstrate too much of this in the paper, but I hope others, will try a creative experiment and publish it. I would love to see that. And I'd included a few sort of snippets from Akeiki's work. I don't think I'll actually read through them in the interests of time, but I just want to make it clear that Akeiki, sometimes his notation is different, but fundamentally lays out most of the ideas that I'll be stepping through. Okay. So that brings us to setting up the paper. And the basic experiment it lays out is the experiment of how we select an objective function. The classic scientific, we have a model, and we're going to tune that model with some test data and we'll tune those same parameters in the model to optimize that objective computed over our test data set. Now, to select the best objective, it's more or less the same experiment. We're just going to flip the variable. And there are a couple ways to do this, but here we're just going to vary the objective function, data held fixed. You can actually vary the objective and the model together, but we'll set that problem aside for now, but that's very common in Bayesian methods. Okay, so we're going to tune the objective function, and now we're going to select the objective, indicating the greatest similarity between the data and the model. We'll formalize this a little more shortly. Now, different objectives have different scales, squared error, we might have mean squared log error, we might have a percentage error, right? And we can't compare these things directly. That's been sort of the traditional problem that people have bumped into, I think, in much of the hydrologic literature on objective functions. So we have to do something, and that's essentially we normalize all of these things to integrate to one, such that they're represented as probability distributions. And in that sense, it's apples to apples. We can compare them almost. Okay, so to maximize information in the model, we're going to select the most likely objective function. Again, that's that sort of probability language, or whichever represents the error in the fewest bits. And throughout the paper, I realize this can be a little confusing, sort of jump between these sort of different paradigms, probability, information theory. But of course, that's what makes this all so beautiful, just that it's general and the general theory. We can talk in one hand about probability, and another we can talk about compression, and it's just the same math. But essentially, we're going to maximize the information to do that in the model, and to do that, we're going to minimize the information in the air. Okay. Talking a lot. I haven't actually done anything yet. Okay. I sort of give some background, build this up from basic principles, information theoretic principles. Maybe that was a mistake. I'm probably, not the person to teach this stuff. I think the basic methodological demonstration is probably what's more important, but nevertheless, I'll give this to hopefully help give some intuition. And that we're going to formulate this task in terms of mutual information between the model predictions and, I'm sorry, I'm just going to shrink. There we go. Model predictions Y and some set of corresponding observations X on this. And I'll try to adapt their notation here. And so this H of X is known as entropy in the data, and we're subtracting off sort of this information in the air, the conditional entropy, and what's left is sort of mutual information, that information shared between the model and the data. And that's what's important. We want to make that as large as possible. Okay. So this trick is very simple. I love simple tricks, but so foundational in all of science. So in practice, we're going to compare two or more models against the same data, right? Such that this H of X is constant. So the first one is Y1 is our model, The second one, y2 is our model, and we're each is the formula of mutual information for x and y1, mutual information for x and y2. Now, what we're interested in, what we're going to look at is actually the relative information between these models. We just want to know, is model 1 better than model 2? And so we can look at the differences. Do that, the h of x term cancels, so that we don't actually need to know, in many instances, the information in the data. We just need this conditional entropy. And what is that? Well, I'm just going to read this, but let x given y, p is given by this equation, which is probably familiar. But that also requires g, this sort of distribution, this true distribution of x given y. But it's the same trick again, we can use an approximate function, f, a likelihood, and then so line 7 gives and it's the difference between sort of the conditional entropy with the true distribution minus that of our sort of approximating distribution. And as long as we're looking at sort of these relative models relatively, that hx given y and g cancels out. We did, in fact, truth cancels out, and able to make inferences with our imperfect model. I won't dwell too much here other than just to introduce some of the notation. That this distribution f is known as the likelihood function. People who've done Bayesian statistics are familiar with this stuff, but it's often denoted with this scrolly capital L. And then very common to take the log of that, denoted as either log L or this little scrolly L. And logging converts, in probability theory, we're multiplying probabilities together, right? So when we take the log, those multiplications turns to sums, and that does a lot of very nice things for us. So finally, where this is all going is this conditional entropy that we're trying to approximate, and this is what Akeki points out, is just the sort of the average log likelihood. Here we divide by natural log of 2 to convert it to bits, from nats to bits, plus this asymptotic term, so that goes to 0 as it increases. Okay, so we want to minimize this sort of information loss, and we can approximate that with the log likelihood. I think that was my recap. The important sort of caveat in all of this is that there's assumption that your approximating model is close to truth. And the more and more you diverge, sort of the more and more kind of noise introduced into this process, the less reliable your estimates will be. So, that's always a caveat, but still, it's very useful. True, we try to come up with the best model we can, and if another good model is deemed better, we have some confidence that it is indeed better. But it's not a perfect system, particularly when we're very far from the truth. So functions like mean squared error, R squared, don't make explicit statements, but become less meaningful as G, our empirical distribution, diverges from the normal distribution. Okay. Textbooks, every statistics textbook will tell you this about them. I think it's too often forgotten in papers in health science, but that's because when we optimize on these things, mean squared error, that's equivalent to optimizing on the normal likelihood. And we'll show that next. So we'll show how to compute the log likelihoods and the AICs of several common objectives. Okay, so de facto mean squared error, that corresponds to the log likelihood of the normal distribution. And you can kind of just see it from this last term here, that as long as the theta is another variable, but it's kind of just a function of this. And so as long as we're minimizing this term, we're minimizing the likelihood, as long as we're minimizing the mean squared error. So these two are equivalent in mass. And here, X are observations, Y are model predictions. Same for mean absolute error. That likelihood of the, and we can go on playing this game, and that's what the paper does in a very simple sense. We can compute likelihoods for other objective functions using simple tricks, like just a change of variables, where basically the new log likelihood is the log likelihood of the transform variable. The log likelihood of a transform variable is equal to passing for the transform variable through original likelihood plus this gradient term. And in a normal change of variables, that's a multiplication, but we're in log, so it's an addition. Okay, so in this way, say if we were to do something trivial like change units, such as meters to feet, this would not change the likelihood. It's invariant in that sense. But there is a wrinkle. It does come up in this paper and will come up more in the future, is that the log likelihood here isn't truly invariant. If we had started with different units, we would have ended up with a different value, right? If we had started in meters, we could convert to feet, and that wouldn't change the value. Or we could start in feet, convert to meters, that wouldn't change the value, but these two values would be different. Normally, we can ignore that in a univariate problem, but it comes back in multivariate problems where we need to decide how to value these disparate things, meters versus Celsius. This gives rise to the Pareto frontier in the value-based paradigm. But I believe, and I think others do, that this is sort of an illusion. In information theory, this doesn't exist. If we're really interested in bits are universal, and this Pareto frontier will disappear if we do this correctly. But I won't get too much into that today. But it goes back, I believe, to the mutual information. Okay, so we established this convergence of the log likelihood to the conditional, and as Akeki points out, this only holds under certain conditions, such as when L is evaluated out of sample. Otherwise, it is sort of biased somewhat. We refer to this bias as overfitting. And the formula for the AIC, I give a modified version here, but it's just the negative log likelihood plus K. Now, when we're just selecting about the objective, K is equal to the number of parameters in the objective. So it doesn't matter how many we have in the model if it's held fixed. And typically with these objectives that I was showing in the paper, there's only one or two parameters, okay? And if you look at this equation, the first term, the likelihood, if you recall, that's gonna grow within the number, order n, the number of observations. So we get more data, that likelihood is gonna grow, whereas K is fixed. And so this relative objectives just is going to eventually disappear. It shouldn't really affect us too much. Nevertheless, we'll go ahead and incorporate it because to be correct, and it's simple enough to do. But for many standard objectives, the overfitting bias becomes negligible. And then the paper, so I bring this all together with a very toy demonstration, and purposely toy for a couple reasons. One, I didn't want to pigeonhole. I want people. Another is there's a federal employee creating models, large amounts of paperwork, and this was a paper I was writing for fun, and I didn't want to use and such to apply this with a more interesting model. So I got creative, And I decided that in this case, the model was just going to take the gauges, two stream gauges, 1,000 or whatever. I think I just used the minimally altered. It doesn't matter. And then the model was to predict flow by rescaling flow from the nearest gauge by the drainage area. So we're not going to do any optimization in this case, although that is a valid application. But we're just asking, okay, given this toy model, this metric, and we choose a good objective function. So the table on the right is 9. There are a couple more in the paper, but we'll just run through a couple. In red, we have mean squared error and the normalized squared error, which is sort of a Nash Sutcliffe, essentially. Mean absolute error, mean square root error, mean squared log error, and the very best, in this case, log error. And you can do a couple things. You can compute a K these, which I do in the paper. Here, I'll just sort of leave it as bits. Again, this is sort of a relative, not necessarily an absolute measure. And that's what's informative here are the difference in bits. And in this case, the best performing objective among, again, these sort of toy objectives, the best one was this mean absolute log error with 7 bits. If you like MSc, which were 11 plus bits, that those additional bits are all noise in the sort of information minimum description length sort of interpretation. And I think that is noise. Just using that term gives people immediate intuition about the effects. Like noise degrades our decision making. It's generally a bad thing. And in this particular problem, mean squared error at least 39% noise, maybe more. So it's a noisy objective. And again, keeping toy demonstrations, what might be the effect of said noise, right? Well, one effect is just your ability to define your objective function itself. And so here I've done sort of a sampling experiment where I've taken different sample sizes, up 0 to 5,000 samples from each of these stream gauges, and for each one, compute the relative error in each of these objectives. And so you can notice a couple things that roughly the lower entropy, the noisier objectives from the previous table, that's reflected here. We can see that noise pretty evidently. So there's a greater sort of spread here, and they also tend to converge more slowly. Whereas, like the mean squared error and Nash Sutcliffe on the top row, whereas the objectives, which are all doing log transformations and things, like by comparison, from the outset, their deviations that we're seeing are minuscule. Even far better than what the objectives like mean squared error and they're given 5,000 observations. Yeah, Dan, what's up? You may be muted.
Thank you. Can you hear me now?
Yep.
Yeah, so I just wanted to confirm what we're showing here. This is basically the entropy of the residuals based on just rescaling from every monitored location from the nearest adjacent monitored one.
Right. So that's this. Yes, it's still calculated for that model. Right?
Okay. Okay.
And we're trying to go ahead.
Sorry, and then so when you compute the entropy of the residuals, then how do you I imagine it's like it's in discrete form, like you compute it, you compute the distribution in discrete form. Is that
I'm using the log likelihood here, right?
okay?
So mean squared error, I'm using the normal log likelihood. Mean absolute error, I'm using Laplacian. For these, I'm using changes of variables. So mean squared log error, I'm just using the change of variables with log.
Okay.
So that one sort of change of variables line, I'm just, over and over again with these toy objectives, applying it to generate these other variants, right?
Okay, thank you.
Yep. And again, this toy example that I gave generalizes, and sort of the current state of the art technique is known as a normalizing flow. And the concept here is just that a normalizing flow is a composition of learnable between some simple random distribution, typically Gaussian. And the key difference here is, like in my toy examples, I'm just applying one, right? But technically, you can do that over and over again. And that's what's shown in the equation on the bottom. This is the same change of variables formula where, here we're applying sort of transformations, composing them over and over again. And then we're adding these gradient terms, one gradient for each transformation. And again, sort of the whole ethos of this talk is just like these simple tricks that you could just like apply over and over again to do powerful things, and normalizing flows that are really interesting application of some of these ideas that is relevant, if you want to potentially deal with more complicated distributions. And in the paper, again, I don't really prove anything. I just give this toy demonstration and then talk about some of the potential implications. The first is just generalization performance. That was the initial motivation in AIC. I'll leave it at that, but many of these other concepts will tie in. Next is uncertainty quantification. How do we, our objective represents our likelihood in the Bayesian sense. It's a representation of a portion of the uncertainty. And we want to use the right representation, particularly when we compute confidence intervals or look at other statistics performance. And so the example here is like, when you're deciding what metric to report, should I be reporting mean squared error, root mean squared error, or R squared, or should I be reporting something like mean absolute percentage error? And frankly, you could probably intuitively like, oh, my errors are growing, increase with X, and so I should look at percentage error, say, which is great, and that can work very well. Too often, people don't even think about it; they just report our mean squared error. And Keiki gives you a simple method for sort of quantifying whether or not that's a good decision. Whether or not a different metric might have been better to use to report your model performance, or to give a sense of its uncertainty. Again, in this paradigm, those two things are synonymous. Finally, this kind of goes back to parameter generalization performance, but the parameter estimation itself. Your model has some parameters in it. How accurately you can estimate them depends on your objective function and how close it is to the true in your model. And this is, if you want to learn more about this, Fisher information, Cramer bound. It's critical there and just coming up with the most accurate model. You want to have the right objectives. It affects the learning rate. In the example, there's two instances of this. Calibration efficiency is the example I give in the paper. where you have a noisy objective, say you're a calibration algorithm and you have a noisy objective. So at each iteration, you're making suboptimal decisions about how to improve the model. And so it should take more iterations to converge. And similarly with the data efficiency, if you have a, model will learn fast. And again, it remains to be demonstrated for whatever particular application you may be working on, how critical this stuff is. At some point, maybe if you just have a powerful enough model and enough data, maybe it becomes less important. But certainly there are domains where it is essential. And then finally, this is a little more abstract, but it also affects compression. And this just goes back to MDL, sort of interpretation where the description length is the length of the model plus the length of the error bits. So, if you have more accurate models, it's allowing for better compression of your data. And if you are able to apply transformations, say, to your data to more standard distributions like the normal distribution, it can allow much better compression of that data. Again, that's a little more hand wavy, but the point of this is just, I think there's lots of potential research topics, and to emphasize that in this paradigm of optimizing general utility, like information, the benefits are going to be very general, kind of whatever you imagine, it will probably affect that in some way. Any application of the model, this should affect its performance. So that's about it. I just mentioned sort of the future work, things that I'm interested in pursuing. As I kind of hinted at this problem of multivariate models and how we go about solving this issue of variables on different scales. That's something I plan to start working on fairly soon. And I know some others are. I'm happy to collaborate more on that. Second are just scoring systems. So today I talked about, of overall performance. But then once you have that, people are often interested in of the model's performance. I think Hoshin has written, others have written about it, but how we create some sort of scoring system. So we first find the overall absolute measure that's best, and then we can decompose that into different metrics, bias, variance, etc., to tell us different things about the model performance. And sort of finally, I do a lot of work on Gaussian processes, which I think are underappreciated in the HydroML community. They're very useful in a lot of applications where we have these very sparse measurements. With machine learning methods, they like complete data sets, and once they have that, they're happy. But very often, that complete data set is an illusion. In fact, you had some scientists going out, and it's based on something much more sparse that is imputed, and somehow the gaps are filled in with some sort of often very crude model to generate your machine learning training set. And I think that sort of stage, it's often behind the curtain. There's a lot of potential for Gaussian process models to sort of improve these sort of data sets that we're using that later feeding into our machine learning approaches. So interested in those things, reach out, and yeah, thank you for your time.
Thank you, Tim. Leila has had to leave, but I guess we can start with questions and comments and discussion.
Yeah, I had a couple questions. So for example, on slide 30, if you go back to that,
One sec. I gotta move my. There we go. One sec.
yeah,
See the
that
slide
one.
number.
So you mentioned this out of sample likelihood and also AIC in the same slide, which is kind of confusing because AIC is in sample. So where's the disconnect there?
Right. Okay. So this convergence between the log likelihood and the conditional entropy, I'm glossing over a couple of details, but it only holds when you're doing like cross validation, right? So if you're doing cross validation, you don't technically need to compute the AIC. And if you are computing it in sample, like, so I have my model, I've calibrated it, and maybe I'm like testing it against, so I have a test data set that I'm evaluating it over, and I'm computing the AIC over that, right? Well, normally when you do that, you're using parameters in the test data set, or learned from the test data set to calibrate that likelihood function. So, in one sense, you're out of sample because you're in the sense of your model, but even when you're sort of evaluating that log likelihood function, you're using information within that data set. You need to account for that. You can get around it by doing yet another cross validation, but I think this approach is simple enough. So you're fitting the parametric distribution to a data set and then evaluating it, and you just need to account for that. And with the parsimony term, the K term.
I used that fact that you say in this first sentence here in one of my papers, but I never included a reference for it. Like, do you have a reference for this statement?
That'd be a Keiki 1974.
Okay.
Yeah, and that's, I was a little hand-waved here, and I didn't read those sections of the paper, but I can share these slides with you. And he kind of, in those few paragraphs, sums it up that in certain, where you're dealing with a particular family, particular model structure and likelihood, all you need is maximum likelihood, right? If you're just considering mean squared error and the one particular model structure, you just need, while you update the parameters, and that's accurate. But when you're dealing with models of different families, either the likelihoods parameters, we have to make this adjustment and that's the extension, the Keiki's extension of the maximum likelihood principle.
Okay, thanks.
I got a question about the experiment you presented us, where you kind of ranked multiple objective functions. Can we go to that slide, please? If I get it right, this means that the mean absolute log error in this experiment you made needs the least amount of information to maximize the likelihood of the data under the same model for all the objective functions.
Right. You want me to explain that, or go ahead?
And how the stream flow works in this, because, well, maybe you used the regular stream flow data, but we know that during the peaks or during droughts, it's harder to forecast and to model. Will this change? Will this rank of objective functions change if we use different types of
Yes.
of regimes?
Yep.
And how do you expect that? How do you
If I
expect
plotted
it
a
to
map, yeah, if I plotted a map, you might see trends. I will say in general, like these log ones, it's typically a competition between, you know, these various log variants that perform best here. And there are spatial trends in that. It can probably vary even within the calibration process. Like when you immediately initialize your model, you have some like very wild errors, and during the course of calibration, that might even change. So that's a more advanced topic. But if we're just sticking with this simple question, and again, being critical of people that just adopt mean squared error, not suck the fruit, is that okay, given a particular data set, in this case, it's a national streamflow data set, what's the most informative sort of metric for that? And if you looked at a particular river, that might vary a little bit, but I necessarily advocate that you have to do this procedure for every time you write a paper. As I say, like intuition does pretty well, you know, using things like mean absolute error or logging. Things that are, you know, in general should give you better performance than just using mean squared error. And so I would like to see more of those things. But particularly those of you who are writing papers, constructing different objective functions, and typically they just they'll give our argument better, but then never any sort of rigorous benchmark of that. I think this fills that niche very well. Like, okay, here's just a very simple method you should be applying if you want to in hydraulic, you say. And I don't think I mentioned this for some of the ad hoc or more informal objective use to represent them as a probability distribution. And so I've, you know, that's a criticism. Nevertheless, I think the noise, I don't think the noise is inescapable. And so even if I don't know how to formulate your distribution or your objective as a distribution, if it's too divergent, it's going to be noisy. It's going to lead to poor results.
And so along the same lines, like in this table, so I think the bits column here is the KL divergence, right?
Yeah. Relative, I think I would call it the conditional entropy. And
Okay, conditional
I
entropy.
think, yeah, that is more accurate. Some of these terms I'm a little hazy and are sometimes used inconsistently, but I think it's safe to say the KL divergence is distinct from conditional entropy.
Okay. And the conditional entropy is measured between the likelihood of the given objective and the probability distribution of the residuals. Is that correct? Empirical.
No. Yeah. So maybe, yeah, maybe I'm hesitant. I'm waffling on whether or not this is a KL divergence. I should think more about that. But it is. Remember that when we compute that, in this instance, you know, what we're computing is this, right? This is what I'm reporting, which is kind of distinct from the divergence in this formula. But what we're actually doing is comparing the relative. So the absolute bits are kind of meaningless in what I presented. We're actually just looking at the relative bits between different ones. And in that case, that truth, the entropy of the sort of empirical likelihood cancels out. You know, when we subtract one of these terms from another, the true distribution cancels out. And so we're just looking at the relative information loss between one approximating model and another approximating model. And that's, you know, presenting it as bits on this slide is a little misleading in that sense. I kind of had some ulterior motives, but maybe I shouldn't have done that. Akechi weights are a very traditional way of presenting this sort of information. The paper gives both.
Yeah, I'm just like still wondering, how do you exactly calculate this then? So you just use the likelihood of the model versus the likelihood of, or the empirical likelihood of the residuals, or is there something else?
You don't use rules. So like mean squared error, I'm using an approximate, I'm just assuming the normal likelihood. And yes, that are from the true empirical distribution. I'm calculating the entropy and the likelihood using the normal distribution. I'm assuming that. In this case, but I'm computing the entropy of the data, whatever the distribution, but I'm using the assuming this Laplacian likelihood. And so, yeah, the assumed effect, but that's okay, because as long as we're looking at the relative differences, as I said, that kind of the truth cancels out. With so long as, you know, we're close. If we're way off, that starts to break down. But that's the general. Help at all?
You cut off for a bit there, but do you have code for this experiment?
Yeah, it's included on the paper. There's a Jupyter notebook, which, you know, I implement each of these likelihoods on the data set. Yeah.
Do you think there are any
questions
implications for like big machine learning models where we might not care about the individual parameters? I mean, likelihood is often about determining parameters, but if we don't care about the parameters, is there still some nice implications for this?
I mean, that is the question, I think. Well, to try it in experiments, like attempt it with, sorry. I'll try this experiment. Objective functions, you know, quickly they converge. Whether it leads to a more accurate solution than another, whether one, you know, how that changes with the volume of data, whether one is more efficient with data than the other. I mean, in extreme sense, that, you know, we can do, but the extreme sense is the unit. If you assume, say, a uniform distributed likelihood, right? And in that case, when you're computing the likelihood, you know, you're throwing out all the data except for the maximum error. So of course that's going to be an inefficient process. And between these, there's a spectrum. And right, when that really becomes costly, it's going to vary through each problem, but it's potentially such a simple thing to correct, right? Nass-Sutcliffe-Sapor objective function. We can make it some simple arguments about what might be a better one. That would be a fairly simple thing to correct in our models. I think, you know, talking with people in the machine learning community, even ones in the hydrologic community, maybe at least, will do things like this behind the scenes. You know, they may assume a different likelihood, but when it comes to publishing their paper, they'll publish mass cycles. So I think it will have application, but I can't say exactly what for each application. But certainly, just in terms of the number of papers generated, people coming up with new objective metrology. If it helps with that problem, if it reduces the number of people that just report an R squared for problems where it's grossly inappropriate, as I've sat through many sessions, just R squared, R squared, R squared, if it affects those things, I think that will be a meaningful contribution. But it might take a while. It might take some more papers from you all to get there.
Is there any other question for Timothy?
I guess I'll have one more maybe. So on the top of that list, we have mean squared percent error.
Mm-hmm.
And in the very beginning of your talk, you talked about how, most people would think that the errors in streamflow are, some form of percentage of streamflow. Does that have any implications for that hypothesis, do you think?
That's an interesting question. This is tricky because, errors are pretty homoscedastic. And the problem, I haven't dug into this, I just assume, but the mean squared percent error here is right. I do clip the data a little bit, but I assume this is blowing up on some zero value. And it still may be useful for much of the hydrograph. And this is a classic problem with log where really so what's done in practice in statistics and hydrology, the hydrologists that use it, is that they will just clip the data at some small value. And yeah, that's not exactly correct argument that doing that outweighs the cost. Now, quantifying that gets a little murky when you're doing things like that. But nevertheless, that is a widely sort of accepted practice. Zeros are when we have these variables that only have positive support, right? They can be zero or large. How you deal with that, because with normal likelihoods and things can go negative. That's not a problem for them, but that's not supported by the data. Whereas we also have log likelihoods, but then things can't be zero, and so there's some fudging going on, and I think that's okay. The point of the paper is just that AIC can kind of give you a simple guide. If you don't trust your own intuition, if you want some guidance about what might be a good metric for a given problem, the AIC is simple to compute for many objectives.
I noticed in the last part of your paper, you mentioned that getting the KGE likelihood was difficult, and I don't doubt it was difficult, but was there a main sticking point that you kind of just gave up on, or
Well,
you didn't know where to start, or what was the issue with calculating the likelihood of KGE?
that was a while ago. I'll start this with my mathematical tricks are pretty simple, and just because I couldn't do it doesn't mean it's not possible. But I believe Jasper Root also wrote a paper saying he couldn't do it, so it's tricky. Another aspect of the KGE, I think, is just how it's formulated, and that there's redundancy in the sorry, I can't keep my terms straight, but it's right. The two variance terms contain some redundant information. And so anytime you have like these correlated terms and you're trying to sum them up, that can be a little tricky, at least for me. If you know how to do it, Jasper would be impressed. So let him know.
Yeah, I'll work on it.
Okay. Well, thanks again, everyone. And I look forward to hearing more about your work in future meetings.
Thank you, Timothy. I'm going to stop the recording now. And I think Layla will upload that later, so we can all disconnect.